Hello. For this session, we're going to discuss the following problem. The instructions are solve the inequality using sign analysis. And the inequality here appears to contain a rational expression that is set to be greater than 0. Now, if we want to solve this type of inequality, there are two main features of a rational function that we need to find. So these features include, number one, the x-intercepts, and number two, the vertical asymptotes. So if we are able to find these features, then we will have an easier time solving this inequality. Now, with a problem like this, we may have to set the inequality to where it is to where we have just 0 on one side. But it looks like here we already have 0 on the right side, so we don't have to worry about that particular step. We just need to determine what the x-intercepts are and what the vertical asymptotes are. Now, to find the x-intercepts of like any function, we would need to determine the x values that make the entire function equal to 0. Now, with rational expressions, we can take a shortcut because we know that if an expression is equal to 0 in the numerator, then the entire rational expression is equal to 0. So really all we have to do is set the numerator equal to 0, and then that will give us the values of x that make the entire function equal to 0. So if we set the numerator equal to 0, we get 3 minus x is equal to 0. Then from here, we would have to solve this equation. Since we have subtracted x from the 3 on the left side, we can go ahead and cancel out that operation. And which operation cancels out subtraction? It is the opposite of subtraction, which is addition. So we're going to go ahead and add. So let's add the x here. And to balance the equation, whatever we do to the left side, we have to do to the right side. So we're going to add the x here as well. We cancel this out. So on the left side, we have just 3 left. And then on the right side, we have 0 plus x. And 0 plus any number is the same number. So we have x like that. Okay, so we have 3 equals x as our solution. And if we want to write it so that x is on the left side, we can just put x is equal to 3. All right, so that is our x-intercept. All right, so this is the value that makes the function equal to 0 for x. All right, so basically, if we plug in 3 for x, then we're going to get 0 in the numerator, and we're going to get 7 in the denominator because we know 3 plus 4 is 7. So that checks out. So we actually end up getting 0 when x is equal to 3. All right, so now let's go ahead and determine the vertical asymptotes. So now to determine the vertical asymptotes, we would set the denominator equal to 0. Yes, but however, we have to be careful because we need to make sure that the rational function has been simplified first by canceling out like any common factors in the numerator and the denominator. It looks like there's nothing that we can cancel out in terms of common factors. So we can go ahead and set the denominator equal to 0. So we have x plus 4 equals 0, and then we'll solve this equation. So to solve this equation, we will consider that we're adding x to the 4. So we need to do the inverse operation of addition, and that is subtraction. So we're going to subtract 4, and we're going to subtract 4. We cancel these out, and we bring down the x, and then 0 minus 4 is -4. All right. So we now have that x is equal to -4, and that is the equation of the vertical asymptote. All right. So we have two numbers here that we can actually use to help us solve this inequality. We have the x-intercept and we have the vertical asymptote. Now, we may ask, why do we need these numbers? Well, the reason is that, like, with the x-intercept, like, we have an opportunity at each x-intercept for the graph to actually, like, switch from, like, having a positive y value to having a negative y value, or having a negative y value to having a positive y value. And we're just trying to see where the function is like greater than 0. So if we know where it switches from being greater than 0 to less than 0, or less than 0 to greater than 0, then that can help us like solve this particular inequality. And also with the vertical asymptote, like we may like depending on the type of like function that we have, like at a particular vertical asymptote, the function may switch from being below the x-axis to above the x-axis, or above the x-axis to below the x-axis. Um, like on the left or right sides of the vertical asymptotes. So if we can identify where the vertical asymptotes are, then we can just test like each side of the vertical asymptote to see if the function actually did change the sign of its y value. All right, so let's go ahead and check out these particular numbers. We can put them onto a number line. So we have -4 here and 3 here. We put the -4 first because it's the lower number, and then 3 is the higher number. All right. So now what we would do is test values that are like on both sides of the vertical asymptote, and test values that are on both sides of the x-intercept. So in essence, we're going to test these three regions. Okay, so first we can choose a number that is less than -4. And a number that's easy to work with that's less than -4 is -5. So we can go ahead and plug -5 into the original inequality and see if it gets us something that's greater than 0. So we have 3 minus -5 over -5 plus 4, which is greater than 0. So now 3 minus -5, if we have minus negative, this actually turns into addition. So that becomes 3 plus 5, because the rule is if you subtract the negative number, that's the same as adding the positive number. So we're going to add 5 to the 3. And then here we bring down the -5 plus 4, which is greater than 0. So now let's go ahead and add 3 plus 5, that's 8. -5 plus 4, that's -1. So now we're going to see if 8 divided by -1 is greater than 0. So if we divide a positive by a negative, that gives us a negative. So we have 8 divided by 1, which is 8, but then it's negative, so that's -8 is greater than 0. But is this true? Well, as we can see, -8 is not greater than 0. So therefore, the region that's less than -4 does not work for this particular inequality as like a solution set. And if we want to, we can just put the sign of what we get. So it looks like we're getting something that's negative whenever x is like less than -4, so we can put the negative sign. Okay, now next um we need to determine a number between -4 and 3 that we can use um to test the inequality. So one number that we can use is 0. So let's go ahead and plug in 0 because 0 is an easy number to work with. It has interesting properties that make it easy for us to solve certain um, equations and inequalities, as well as simplify expressions. So we have 3 minus 0 over 0 plus 4, which is greater than 0. So 3 minus 0 is 3. 0 plus 4 is 4, and that is greater than 0. So now, um, so now we have to ask ourselves, is 3/4 greater than 0? Yes, it is. So we know that this region actually would work, and also the sign that we get when we choose a number from this region and implement that number into the like expression is positive. All right. So now let's choose a number that's greater than 3. A number that's easy to work with that's greater than 3 is 4. So let's go ahead and plug 4 into the inequality. So we have 3 minus 4 over 4 plus 4, which is greater than 0. All right. So now 3 minus 4, that's -1. 4 plus 4, that's 8. All right. And then we have to determine if -1/8 is greater than 0. But is this greater than 0? Well, we can see that it's not. Yeah, so therefore, we know that anything that is greater than 3 would not work for the inequality. And also, we get a negative number if we plug in anything that is greater than 3. So, so now let's go ahead and determine the solution set. So, so basically, if we want to, we can write our solution in interval notation. To write it in interval notation, we would just say that anything from -4 to 3 would work for this inequality. So we will put -4, comma 3, and then we have to see like if we're going to use brackets or parentheses, as well as where we would place the brackets or the parentheses. So we see here that we're dealing with like greater than 0. Since it's greater than, we know it cannot equal 0. And and um and we already know that like the function equals 0. when x is equal to 3. Um, so basically we know that we're not including the 3. So we can go ahead and put a parenthesis here. Now at the -4, this is actually the x value of the vertical asymptote, and we never include like the x value of the vertical asymptote. So this is going to be a parenthesis by default. So now we have our interval notation. So basically it is from -4 to 3, but not including -4 and not including 3. All right, so that is how we would solve this type of problem.